So it is a great pleasure for me to introduce the next speaker, the first speaker of this session, Dr. Claudio Muñoz, who will give a talk on nonlinear stability for MKDV breathers.
Okay, thank you so much for the presentation and the invitation to the organizers. It's a great pleasure to be here. This is my first time in Rio, so really nice. Okay. So today I'm going to talk about a recent result with Miguel Ángel Alejo concerning the stability of a very particular kind of solution of a dispersive equation. So if you have a question, just tell me. I'll try to go slowly. So I will start out with the following equation, the modified Carteret debris equation on R, which is written here. So it's a 1D equation, very simple equation, ut plus uxx plus u to the power 3, derivative of that equals 0. And u is a function depending on x and t is the time, and it's real valued. So from now on, I will call MKDV this equation. This equation is globally well posed for H1 initial data that come back to Kenny, Ponce, and Vega. So if the initial data is in H1, then the solution is always in H1 for all time. And not only that, the norm is conserved, is constant, is bounded, sorry. Because there are two conserved quantities associated to this equation. So the first one is an L2 conserved quantity called the mass, m of u, and the second one is the so-called energy, which is written here. So remember, we're working in subcritical regularity, so everything is good here. So everything is well controlled. So these two quantities are conserved. The second ingredient of my talk is are solitons. So MKDV has a special solution called solitons. So a soliton is a profile of the form QC of x minus CT minus x naught, where x naught is a real number and C is a positive parameter, the so-called scaling. And QC is a function of the form square root of C, Q of square root of C, S. And Q is explicit, it's just square root of 2 sec of S. And QC is the unique solution of the nonlinear ODE Q second minus CQC plus QCQ equals 0. Among the class of positive function in H1. That's important. These solutions, so, well, I have a picture, but let's wait some moments. So a soliton is a profile moving to the right with positive velocity. What is important is that the size of this solution is proportional to the velocity. Okay? It's a very nice guide. So, well, a nice question is the following. Is this solution stable? By stable, I mean the following. So I assume that I have an initial data U0, which is close enough to a soliton in H1, given by this quantity alpha. And then it can be proved that the solution of the initial value problem is always close to a soliton profile, right? So it's the same profile, but with a different position, rho of t, depending on time. But what is important is the fact that the derivative of such a profile is near the initial velocity. So it can be, it could happen that rho of t has a logarithmic correction, okay, of ct, which is the original velocity. But the derivative of a logarithm is decreasing in time. So that's the important point. So these results are due to Benjamin, Bonas, Suganidis, Strauss, in the case of KDV, an equation that I'm not considering here. But the full proof is due to Weinstein under the assumption of global well-posedness in H1, which has been fulfilled by Koenig, Pons, and Vega. Okay. Let's talk about more special solutions. So MKDB has a nice property. It's an integrable equation, which means that it has an infinite number of conserved quantities. For instance, the H2 conserved quantity is given by this formula here, f of u, written down here. And of course, there is global well-posedness for H2 initial data due to this quantity. Okay. Moreover, there are solutions describing the elastic interaction of several solitons at the same time. Okay, the so-called multi-solitons. And this is wonderful because this is true even if the equation is not linear. So the behavior is linear in some sense. And these solutions are H1 stable. In the case of the KDB equation that has been proved by Lax and Maddox-Sachs, and in a more general case, that goes back to Martin, Mel, and Sai. So if you want a picture, well, a so-called two-soliton is a guy of this form. So there is a guy with velocity c1 and another one with velocity c2. And what is important is that c1 is larger than c2. And this is the behavior as t tends to negative infinity. So the idea is that these two guys have to collide at some point, at some time. And then the miracle is the following. They stayed, as in the previous lecture, did you see the picons? Okay, that's the same thing. So the same guy, QC1 here, and QC2, and nothing more. Okay? So in that sense, the collision is elastic. Okay, but today I'm going to consider the following very special solution of MKDB, the so-called breather. A breather is a solution which is also localized, but it has an oscillation mode. Okay, so the explicit formula is given here. It has four parameters, three parameters, right? Two scaling alpha and beta, and two translation parameter x1 and x2. Okay, so that's the formula. And what is important for us is the fact that the guy called gamma, did you see gamma there? Gamma represents, well, negative gamma represents the velocity. Okay, so gamma can be either positive or negative, okay? Which means that breathers can move to the right or to the left, or they can be static, okay, if gamma is 0. So here I have some pictures. So first, on the left, we have a soliton, and on the right, we have a breather. A breather with alpha equals 9 and beta equals 1. So you have to remember that alpha is some kind of oscillation parameter. So alpha larger means that the breather oscillates a lot. And the velocity here is negative, so this guy is moving to the left. Okay? So, okay. Why are breathers interesting? Well, so this is just motivation, it's not mathematics, okay? So breathers are present only in a very particular models, okay? And all these guys are integrable, okay? So in addition to the MKDB case, we have the Sine-Gordon equation written here. Now something about mathematics. The MKDB breather has been used to prove that the MKDB flow map is not uniformly continuous in HS with S less than 1/4. Okay, so that's a result of Koenig, Pons, and Vega. And finally, we have that using the inverse scattering theory, since the equation is integrable, it can be solved explicitly, and sure prove that rapidly decaying initial data decompose into solitons, multi-solitons, and breeders and radiation. Okay? So at least from the point of view of the inverse scattering theory, breeders have to appear from very general initial data, which suggests that they are maybe stable. Okay? So, but, well, let's try to prove that in a rigorous way. Okay? So, there are two questions. Maybe the most important question is the second one. Which are the allowed perturbations that make this true? So some previous results. So first of all, there are numerical computations that suggest that the answer is positive. Okay, that's a result of Gorilla, Alejo, and Vega. The corresponding lattice breeder, so the so-called space periodical breeder, is actually unstable. And there are some results concerning the Sine-Gordon case, but they are different in nature. I mean, Birnir, McKinnon, Weinstein, and Densler perturb the equation, and they prove that there are no breeders if the perturbation is non-trivial, okay? The same problem for the MKDB case is open. We don't know how to prove that. So let me try to tell you why, if we consider H2 perturbation, the problem is easier for the stability problem. So in order to do that, I have to remind you more or less the proof of the stability of a soliton. Okay? Remember that a soliton is stable under H1 perturbations. So a soliton satisfies this nonlinear equation QC second prime minus CQC plus QCQ equals 0. And that's quite important, really important. A soliton profile satisfies a nonlinear ODE. Okay? And that comes back to, that's because of the following fact. The fact that you can construct a Lyapunov functional, H of U, composed of the energy plus C times the mass of U, which is written down here. And in such a way that if you write down your solution U in terms of QC, the soliton, plus term C, and then you expand this functional around the soliton, what you get is a constant, the energy of a soliton plus C times the mass of the soliton, minus an integral of a first order term C times the equation of the soliton. So this term is 0. And what you get is just, if you want to study the nature of this extremal point, the soliton, then you have to study the second order operator Q of C. Okay? So, well, do breeder profiles satisfy an elliptic equation? And the answer is yes. But it's not actually an equation of like the soliton one, right? Because there is uniqueness. Okay? If the same equation, then it's a soliton. So don't expect a miracle. The equation is this one. It's a four-order equation. It's still an ODE. So for any time, any x1 and x2 real numbers and any alpha and beta scaling parameter, a breeder satisfies this nonlinear ODE. Okay? So how much time do I have?
You have 10 minutes.
10 minutes, okay. So let me try to prove this result. Well, let's sketch the proof. So first of all, you have to work a lot because the breeder is somehow a nightmare, okay? It's hard to manage. But, I mean, if you work a lot, I mean, you will find that the integral of b squared is an explicit expression. So I wrote explicit because at the beginning I wrote this in this here, it didn't fit. So anyway, it's explicit. So, but what is important is the fact that the mass, when you take x tends to infinity, the mass of a breather depends only on one parameter, the parameter beta. So it's independent of alpha, which means that it has some kind of instability with respect to oscillations. The energy can be also computed and is depending on beta and the parameter gamma. So if gamma is positive, then the energy is positive, and if gamma is negative, then the energy is negative. And the third important point is the fact that the breather is a derivative of an L infinity function. So if you come back, I will come back to the original definition of the breather. Here you can see that there is a derivative, right, of an L infinity function. That's important in some sense because it simplifies the computations in such a way that you can integrate the original equation of a breather, right? That's the first equation. Then you multiply this equation by bx and integrate on x, and you get the second equation. And finally, you have to compute this guy, the third guy, by hand. So, kiss your mother and try and start. I mean, what you have to do. So the third quantity has to be computed by hand. So now we compute the original equation. So first of all, we replace b2x. I mean, you have b for x. So b for x is b2x, xx, right? So replace b2x with the first equation here, bxx plus b cubed equals negative b tilde t, sorry. And replace here and go beyond, I mean, go ahead. So what you get is the third line here. And what is important now is that you replace the second term has a bx squared. Did you see that? Bx squared. So you replace bx squared using the second equation. What you get at the end is the final line. Did you see the final line? The final line is 0. Okay? So that's all. Okay? So some consequences. The first consequence is the fact that the breather has 3 parameters. So if you take derivatives with respect to the parameters, x1 and x2, then these 2 linearly independent functions are part of a kernel of the operator written down here. Okay? So now what we want to prove, we want to get the spectral properties of this linear operator. And the kernel of this linear operator is spanned by B1 and B2 because the other 2 guys in the kernel are exponentially growing, so they are not in L2. The continuous spectrum depends on alpha and beta, so it's always away from 0, that's important. And that's because L, the operator L, is just a compact perturbation of a constant coefficient operator, written down here, okay? So, and finally, L has a unique negative eigenvalue. This is very important. I mean, this is the main point of the proof, which is uniformly away from 0 with respect to time, okay? And it has an associated eigenfunction b minus 1. So, how do we guess this? Well, formally, if you consider the associated quadratic form to L, for H2 data, and using the equation for B, so let's come back to the equation, here is in red, and you take derivative with respect to the scaling parameters, alpha and beta, you get 2 equations. an equation for the derivative with respect to alpha, and another equation for the derivative with respect to beta. Okay? That's just a computation. But what is important now is that if you compute this quadratic functional on these two directions, what you get is something incredible. I mean, for the derivative with respect to alpha, you get something positive, which is surprising because you know that the scaling directions are somehow negative in the real case. And for the derivative with respect to beta, you get something negative. So actually, under high regularity assumptions, alpha behaves as a positive direction, so a good guy. So the proof of that, if you want to prove this rigorously, we have to consider the so-called Wronskian of B1 and B2. Okay? It turns out that the number of negative eigenvalues of the operator L is given by this sum of the dimension of the kernel of W, this Wronskian, for all x in R. Okay? It turns out if you want to compute, the kernel is different from 0 if the determinant is 0. So if you compute the determinant, you get something beautiful. Okay? So it turns out that for all time, this quantity is 0 at exactly 1 point. Okay? So just 1 point. And what is important is the fact that at that point, this Wronskian, this matrix is not identically 0. So the dimension is not 2. It's just 1. Okay? So that's the main point. Let's go back to a result of Greenberg. I didn't put this here. I'm sorry. So the conclusion is the following. If you are orthogonal to these three instability directions, then you are coercive in H2, right? So if you initial that, if you data C is orthogonal to B1, B2, and B minus 1, the negative eigenfunction, then you are coercive. And the first two orthogonality conditions can be ensured if you modulate with respect to time the translation parameter x1 and x2. Okay, but the problem is the third one, the negative eigenvalue. So what we need is a weaker version of this result. If you had just two orthogonality conditions, then you have something a little bit different, but with some good guy. We replace B minus 1 by B, right? And why B is better? B is better because now we can use the mass conservation to write down an explicit formula for the integral of C times B at time t, depending on good guys. The guy at 0, which is constant in some sense, and quadratic terms, right? So everything is okay. This is a good guy. It's going to help us. And finally, the last part of the proof is, well, the introduction of a Lyapunov functional, a new Lyapunov functional adapted to the breeder case. So this functional is composed, well, here is when we use the fact that we are working with H2 solutions, okay? So we use the second order, the H2 conserved quantities plus a linear combination of the energy and the mass, okay? And this kind of functional goes back to Lax, Maddox-Sachs for the KDB case, considering two solitons. Capitula in the case of NLS, Lopez-Neves in the case of Benjamin Ono, and very recently Hormel, Perelman, and Swirsky in the case of two solitons of KDB. Okay? But the functional is here, and now if you expand this functional around a breeder, what you get is something which is constant, the functional at the breeder, plus a first order term, which is actually 0. It's the equation of the breeder. Okay? And finally, a second order functional, which is the same as before, Q of C. And using the coercivity property, you find out that Q of C can be bounded below by CT squared in H2. So comparing at two different times, you get that you can bound the the perturbation terms, all in terms of the initial one. So the final conclusion is that breeders are orbitally stable under small h2 perturbations. Thank you so much.